Quite a few people have built real transformers, but not many people can ride in their transformer because a car's basically an empty box full of seats and passengers. In order to get the robot in, there's no more space for any people. So I'm going to build a real transformer, but instead of riding in it, I'm going to ride on it, just like one of those kids' Power Wheels cars. As usual, I've already done it, so you better buckle up for a very exciting build. I really want to give my transformer all its arms and legs with proper knees and elbows rather than just some parallel 4-bar link that pushes the front of the car up to make the body of the robot. It'll need quite a lot of torque at the ankles and knees though, so I'm going to use similar motors and gear reductions to the mini AT-AT I built, which was very powerful. It could lift itself and me on just 2 legs, and I couldn't physically stop the joints moving when it was running. These are 100:1 gearhead motors from Gimson Robotics, with a further 3D printed 2-stage reduction to get to the final joint. We need 6 of these assemblies in total for all of the 3 leg joints, so we better get printing. Just a quick ad from my 3D printing sponsor, thanks to Lolzbot 3D printers for supporting my channel with 3D printers. I've got the latest Lolzbot TAS 8 here, which has linear bearings for the main axes, a graphical LCD touchscreen for control, a BL touch for levelling, and as you can see it's got dual extruders. Check out later in the video for some more dual extruder action, but for now I've got lots of mechanical parts to make for this project. I'm also using the Lolzbot TAS long bed with a 1.2mm nozzle for some really big chunky parts, and the Lolzbot Mini 3 for lots of detail parts. I need to fit bearings into some of these parts made with a 1.2mm nozzle, so I've made a tolerance part with a thinner nozzle that fits in, and that means I don't have to reprint the whole part if the holes are wrong size. Thanks to Simply Bearings for the bearings for this project. I also used some collar clamps which came from Simply Bearings, and there's some bigger ones later in the video. The majority of the mechanical structure for this robot is held together with 3D printed plates and then T-nuts and socket caps, which are M5s, screwed into the T-slot of the extrusion, and I've used sort of box sections here to make up most of the structure to make it really rigid. You can kind of see some joints emerging here with a bearing in the middle of a gear and then a bearing on the other side, and then all of these plates on the side which hold everything super rigid. This is the foot for the robot, a drive wheel will be in that groove, and this whole thing needs to be quite rigid. This is one of the other joints which I've made here, and you can see we've got several holes here, one for a motor and one actually for a 20mm steel shaft which will be one of the main joints. And these joints repeat for the ankle, knee and hip. Here are those Gimson Robotics motors again, which are actually 99.5:1, not 100:1, but they have a keyway and most of this is gearbox and the motor's just the piece at the back. Those fit into the 3D print and then I can clamp it down to hold them, but we also have a place for a faceplate which is going to fit on there, so it absolutely doesn't rotate in its slot. The next stage is of course putting a gear on there which is 3D printed, and that has a captive nut and a grub screw and also a keyway which aligns with the keyway of the motor. So I can put my 4mm key in and tighten up that grub screw, and that will hold the gear onto the motor pretty well. It's actually quite hard to backdrive these motors with such a high reduction already. Now we can insert our 20mm steel bar and tighten that up with 2 bolts, and this is actually going to make the main joint for one of the robot axes. On the back of that though is a 3D printed piece, and that gets screwed on so it's perfectly in line with that 20mm steel bar, and you'll notice in fact that there's a piece of metal in the middle of there press fitted in, and that in fact is a magnet, and we'll come on to why that's there slightly later. What's really important is that those are perfectly in line, so one half of the joint is metal and the other half is plastic with a magnet in the middle. We have an intermediate gear which fits onto a piece of 8mm steel shaft, and that of course meshes with the gear on the motor and will eventually mesh with the big white gears you've seen already. Thanks again to Simply Bearings for the collar clamps which are used extensively throughout this project. So we've now got the piece with the motor and its gear on, with an intermediate gear and the big gear, so we've now got a joint basically. You can see the 3 gears there, and now if I backdrive this is actually quite difficult because we've got quite a high reduction and we're trying to already backdrive that motor with its 100:1 gear head on or thereabouts, so that feels like it's incredibly stiff and I've got hardly any backlash, which is what we need. It's pretty hard to backdrive, but I've got a battery here, it's just a 12-volt LiPo, so I'm going to put some power on it and try and hold this down, see how strong it is. I'm going to have to do this with my elbow whilst holding the battery. Right. Okay, that's pretty strong. Just coming back to those magnets for a moment, you'll notice they move perfectly with the joint of the robot, and that's really critical for later on. There is a bit of backlash in this, but most of that actually seems to be backlash in the gearbox, which is the metal gearbox on the motors, There is a little bit in the big gears, but actually it's going to be perfectly fine for our application. So I've got another one of those, which means we've got 2 transformer feet, or at least the ankles. So now we need to do the knees and the hips, which are built in exactly the same way, with the same motors, the same intermediate gear, and a big gear that's going to move the next piece of extrusion. So I'm just going to put those together. It's exactly the same assembly, and then we'll see what we've got all together. The next joint up is the knee joint, and of course that goes above the ankle joint, and then that stick on top is the thigh, and then on top of that we've got another joint, and that's going to be the hip joint, and so the stick right on top now is the main body joint. So I've been making 2 legs all along, so we've got an identical pair, only they're mirrored of course, and we've got 6 joints with 6 encoders, and everything's built the same. So this feels pretty sturdy at the moment. There are gaps in between the pieces where it's folded up, so we could put extra blocks in there to support it, but I really want to see if this is strong enough to hold my weight, to see if we can ride on it. Yep, that feels pretty strong, and I'm actually sitting with a gap in between 2 of the hinged pieces here as well. So actually these close onto their own sort of blocks and they can't go any further, so they close onto end stops. And that's strong enough for me to sit on. So this is pretty hopeful. It's now time to work out why we put magnets in. These are AS5047 magnetic encoders, which we put adjacent to that magnet. These are SPI devices, and they basically measure the position of each joint. They're all wired in with long cables. They're not really supposed to be, but they do work. And those are wired into a teensy, and I've wired in both sets of those. So now we can measure the angles of all of those joints, and we can then turn everything into a massive servo. The cables are unshielded, and that works for now, but we'll see if we need to go and replace them once there's some PWM and motor power whizzing about. I've got some BTS 7960 motor drivers, which are more than powerful enough to handle those motors. There's 6 of course, and that's 1 for each of the motors. Each of those motor drivers is mounted right next to the motor, so I'm going to run PWM down adjacent to those SPI wires, and also motor power. Of course, all those wires run all around the legs, and then they run into the teensy. Everything PWM and SPI and motor power comes down from the power distribution. I've got 2 3S LiPos in parallel with an E-stop, and that switches a relay and then turns power on and off to everything. So I've set up some code to make these into a servo, so now I've got 2 buttons I can press, and that'll send it from one position to another, and that seems to be working pretty well. But obviously the motor's going at full speed to get there. It does decelerate as the error is smaller as it reaches its target, but it's actually far too quick. And what we really need to do is coordinate multiple motions in this transformer, like we did with the AT-AT. And it was highly critical that all the legs were synchronised so that it moves smoothly along the ground, with one leg getting shorter and taking a step, and all of the legs cascading so it didn't tear itself apart. So you can see there we've actually got all of the legs slowly moving in one direction, and then one leg will go and take a step. And I did that using interpolation, so we slowly move from one position to another rather than just making a harsh step change. But there's a library for that called ramp, and you can see my green line there is my step change, my sudden change that I'm putting into it, and my blue line on the output is my gradual change, which is slowly interpolating between the start and end points over a specific amount of time. And that relates to the position of the motor, so that would drive our position, and our motor can move much more smoothly and slowly over a set period. So here's our new gradual response, which is ramped, and it's much slower and much more gradual. We've still got a proportional response that slows it down as it gets to the end because there's less error and therefore less velocity. And that's the second joint working, which will be the knee joint. So that's working lovely as well with our transform up and down buttons, which are eventually going to control the whole robot. And finally the ankle joint, and I think these motors are going to be more than strong enough. We've got a really lovely response and a really lovely gradual motion. Right, I've got 2 buttons to do the main transformation now. So I've got one, if I press it there's a short delay so I can step back and I don't need a remote control. Then we should see the body go up, and then all of the rest of the joints interpolate at once until it comes up at full height. Now obviously we've got a lot more transforming sections to put on here, including the head and the arms and all the other bits and pieces, but that's basically going to be about the size of a human, and then we can transform it back down again. And then I'll be able to get on and ride away. But before we put the wheels on, it's time for a quick ad from the video's sponsor, which is PCBWay. PCBWay is a one-stop shop for PCB manufacturing, assembly, but also other types of manufacturing services, including contract manufacturing, all under the same roof. PCBWay manufactures all sorts of printed circuit boards, but PCBWay don't just make PCBs, they also provide parts manufacturing services, including online CNC machining, sheet metal fabrication, 3D printing and injection moulding. PCBWay's 3D printing services include SLS, SLA, DLP, FDM in a variety of materials, including various resins, nylon, PLA, ABS, TPU, PEEK and more. There are also various surface finishes available, including painting and even electroplating. PCBWay support various proofing methods available to each material. The CNC machining services include a wide range of materials, including aluminium, stainless steel and various plastics. They can fit inserts and tap threads and provide a whole variety of surface finishes, including brushing, painting, powder coating and anodizing. PCBWay actually made some aluminium parts for one of my previous projects, the omnidirectional ball wheel bike. These were just CNC aluminium plates, but they can of course make multi-axis CNC parts as well. Check out more now at PCBWay.com, and I'll put that link in the description to this video as well. On the back, I've got two 10-inch hoverboard wheels held on with their existing brackets into my 3D print and through the metal, and then we've got two casters on the front, and hopefully we can differential drive. But for now I can push along, and it goes really well, so I think when those hoverboard wheels are under power, it's going to be really fast. But we've still got a lot of features to add and a lot of mechanisms to build, specifically to spread out those shoulders so they fit round the bonnet when the bonnet flips down to make the chest. So to do that, I've got some V wheels which fit into the V slot of some extrusion, and that's going to make a nice slider so we can slide those arms out sideways. Now I've got two of those, one for each arm, and those slide really well and they're fitted on there quite well, but we need something to push it. So I'm going to be using some Dynamixel servos, which Robotis gave me a while ago and I've been recycling in lots of projects, but we're going to gear those down, so we've got a gear fitted on there, and then each joint is going to have another gear, so we've got roughly a 2-to-1, and those are fitted on really tight with hardly any backlash, and that's going to give us a really powerful joint. The servos are around 100 kilograms centimeters, so we get about 200 kilograms centimeters of torque. My arms slot onto that V-slot extrusion, which is fitted on our body frame, and that means those arms can spread out as it transforms, and then its arms will be able to reach around the sides of the bonnet. To push those in and out is a very simple but effective mechanism. We've got just a big servo horn 3D printed and put on that servo, and then it's going to push those arms out sideways and pull them in again. There we go, so that seems to be working quite well, and I just put another bit of 2020 extrusion to mount that servo on. My elbow joint and also my shoulder joints are also geared Dynamixels, so we've got lots of torque there, and that means we can fold it up and carry any body panels and anything else. So we should have tons of power and everything's looking good. So here's the whole assembly with all of its joints in, apart from the head and a few other things that are going to operate panels. So Dynamixels are quite expensive. I've run out of them for this project, so I'm using some 270-degree servos, which I got, which were about £20 each, for about 20 kilograms centimeters of torque, and these are again geared down 2-to-1, so we get roughly 135 degrees of motion at about 40 kilogram centimeter torque. I've got a little cap that fits on there to hold a bearing in the end of the gear, so they're nice and strong, and these are actually going to operate the bonnet that flips up and down and becomes the chest of the robot. I've now fitted the Dynamixel shield, and the Dynamixels run off 12 volts, however the other servos need 6 volts, so I've got two 6-volt regulators with the blue lights on there to power those. So if I now go and press the magic button to transform up, which is temporarily taped on the side, we should see the body folds up, and we should see those shoulders sliding out to extend, the arms unfolding, and finally the bonnet folding down to make the chest of the robot. It's got no head yet, but that's coming later. So that looks about the right proportions, and if I press the button again to go down, then it should fold down in reverse order, and some of this is going to need to be sequenced so that the panels don't crash into each other, and that's actually going to be quite a hard challenge to fit everything together. So pretty happy with my naked transformer so far. Obviously we do need a head, which is going to be another geared Dynamixel. That's going to flip up as the bonnet flips down, and there's some panels around the back and some other things that need some servos, as well as some hands that are going to fold out, some other bits and pieces, and all the body panels. But I'm pretty happy with that for now. This is my head stick, which is another geared Dynamixel that's going to flip the head up, and we need to sync that up with the bonnet so they don't crash into each other. Some of the panels are really hard to get clearance against adjacent panels and move them out of the way of the rest of the mechanism. So I've prototyped this Lego mechanism. You'll notice the yellow beam on the top there moves completely almost upside down and completely clears the side, which is basically that red beam, so we can move it completely out of the way and something else can happen. So I've prototyped this up with the remaining Dynamixel servos. So we've got the panel on the top there, that'll have a big panel on, and that's going to move completely out of the way of where it was and completely out of the adjacent panel on the side. And I've used these at the back here to move the whole of the back of the robot out of the way so it can actually stand up. But of course there are lots of mechanisms and panels to make, including folding hands and the head, and all those parts have to be mechanically synchronised so that they can fold out without colliding with each other. I printed various parts for the head which assemble in sections, and I thought I'd give that a lick of silver paint. The front wheels are of course fake because I'm actually driving on casters, and those end up at the elbow of the robot. I'm really happy with how the arms fold out and where the wheels end up, and it looks like that head and bonnet or hood are going to align. I really love how it folds up when the shoulders contract back in and it finally folds down, and I think this is going to be pretty cool when all the panels are on. My hands fold up and they don't have any motors, so I'm just going to rely on gravity to slide them up and down the forearms as the arms move when it folds up and down. So now we just need to make lots of car and robot body panels, which are going to be partially foam board with 3D printed wheel arches and other bits and pieces. And I'm going for a futuristic armoured cybercar type of look for this one, because there's no space for the people inside anyway to look out of the windows. A bit of ducting always looks good. And of course some blue LEDs always set off a sci-fi build. I've got two cheap e-bike ESCs on the back here, and then I've got two of these little thumb grip things I'm going to put on the front to drive it, and hopefully, because I've got two wheels and casters, I'll be able to steer with differential drive and turn around corners by just running one wheel. It's time to make the Not the Transformers logo for the front of the car, and for this I'm using dual colours and dual extruders on the Lulzbot Taz 8. And when you switch extruders, it actually physically raises one and then puts the other one down, does a little purge and then carries on printing. And that makes a much cleaner job because the other nozzle isn't right there, oozing filament of the wrong colour or material all over the part.
Well, it's super fun to drive, but I could do with some brakes really, and I could really do with some brakes or something to slow down one wheel. I thought I could differential drive and just make one wheel go faster, but with these motor controllers, the other one just three wheels and carries on going and I can't steer. Obviously it turns into a robot, but it doesn't walk, and that's not really in scope for this project because walking robots this big are really hard. But what we could do with is driving it standing up, and I was going to do that. I thought it'd be really unstable sideways. So what we really need to do, as well as spreading the shoulders, would be to spread the legs out. And the easiest way to do that would be if we had Omni wheels on the back, because of course these wheels can't move sideways, but then we might as well have 4 Omni wheels and have an omnidirectional robot that can move in all directions and actually drive on its front wheels instead of these silly casters. But that's for another project.